For letting me speak at this event. It's nice to get to pay tribute to Voevodsky's ideas. So this talk is really inspired by the last conversation that I had with Vladimir and also the first one. And so the last conversation was at a big proof meeting in Cambridge last summer. And I was sitting outside and talking to Vladimir, and the thing that, I don't remember exactly what he said, but the thing that I took away from it was a sense for how he was very excited about a very small thing. So there was like an abstraction in the course of his large project on doing the semantics of type theory in a way that would be more familiar and feel more solid to mathematicians. And in the course of that work, he'd uncovered a very small abstraction that was much less than a category with families or a category C system or that kind of thing. It was just a tiny piece of it. And in terms of that tiny piece of it, there was some really nice mathematics that they were doing in the formalization. And what I took away from that was that he was very excited about kind of the beauty in getting the details exactly right for this very small thing. And that was exciting to me to see someone who had such big thoughts about, working at a very high level of abstraction, working top down and putting together areas of mathematics and working at that very high level of abstraction, also being so excited about the details of things. And that was the last time that I talked to him. The first time was at this meeting at CMU that Mike mentioned yesterday. And at the time, so I was a PhD student then, and I didn't have the mathematical sophistication to be wowed by a definition of contractibility that didn't use infinite coherence or something like that. What I remember from that meeting was Vladimir put some computer code on the screen, some Coq code. And the thing that was surprising to me at the time, interesting to me, was that he'd managed to take stuff that I thought I understood as someone with a background in type theory and present it in such a way where all the words were renamed to something completely unfamiliar. For example, sigma types were called total 2, and identity types were now called path. And so there was this whole world opening up because of that. So in the spirit of that, part of what I'd like to do today is to actually show you some examples in a proof assistant in a notation that you'll hopefully find totally unfamiliar. But before we do that, I want to do a little bit of background on what type theory is and give you a sense for what these kinds of projects look like. So type theory, Martin-Löf type theory, is the basis of a bunch of proof assistants. And there's different flavors of type theory and different kinds of proof assistants based on them. But one thing that they all have in common is that there's some idea in these type theories that proofs are programs in a certain sense. And to get you to understand that idea to the point where I can talk a little bit about the questions that have come up from a computer science point of view in understanding univalence, I want to do a very simple example, which is to define the natural numbers and define the doubling function on the natural numbers. So 0 goes to 0, successor of n goes to double successor of double n. And then define what it means to be even. That is, a natural number is even if here's some type, and a natural number is odd if here's some type. And the way to read this notation is that this says there exists a k such that n is equal to 2k plus 1. Okay, like I won't trust that you can actually parse the notation that's in the type theory, but that's what this notation means. And similarly, even means that there exists a k such that n is equal to 2k. And given these definitions, we can prove that every natural number is even or odd. Okay? And if you're a type theorist, the way that you prove that every natural number is even or odd is you do a proof by induction, and you say 0 is even. And in the inductive case, you say n is either even or odd. Therefore, we have to show that n plus 1 is either even or odd. Well, if n was even, then n plus 1 is equal to 2k plus 1, where n was equal to 2k, so it's odd. If n was odd, then n plus 1 is equal to 2k plus 2, where that's 2k plus 1, and therefore n is even. Okay. So the question is, if we type this into a proof assistant, here's the code. This is literally the same thing I said on the previous slide. You don't need to understand the symbols, but that was that proof by induction. Then the question is, if you prove for all n is even or n is odd, then, and proofs are programs, what program is this? Okay, so what are we computing when we prove that every natural number is even or n is odd? And a good way to answer that question, if you have a program, is that you can run it. So here in this file is the definitions that I put on the slide. It defines the natural numbers there, and it gives nice names, n0, n1, n2, and so on for each natural number up to 20, because writing 20 successors gets a little bit tedious. And then it defines the double function and even and odd, and then this screen full is the proof. And then we can load this over here, and then even or odd is a function, so we can run it, and we can ask, for example, suppose I ask, is 0 even or odd? Then it comes back and it says, in left, 0 something. And I can run it on 1, and it says, in right, 0 something. And I can run it on 2, and it comes back, in left, successor of 0 something. OK. So any guesses for what we've computed so far? Yep. So first of all, the number here looks like the k that we said exists over here, right? We said even is there exists a k such that n equals 2k, odd is exists a k such that n equals 2k plus 1. Well, a constructive proof of an exists includes the k. So we're computing the k. The in left and in right here, think of these as the left and right injections into a coproduct. What we're doing there is we're computing the parity. So if you have a constructive proof that n is even or n is odd, then from that we're getting the bit which says, was it even or was it odd? So let me go back to the slides now and just talk through it a bit. So what we're doing is we're interpreting a for all as a function, an or as a coproduct, and then the coproduct injection in left or in right that we get is determining whether the parity was even or odd. And you can see that what we're doing is we're mapping left to right and right to left, which is saying that the parity bit flips every time we go through the induction, which is telling us that we're computing the parity there. And then you can see that in one of these cases, we increment the k here, right here, or here. So this goes to successor of that, 1 plus. Here we keep it the same, which means that what we're computing, you can think of it as the floor of n divided by 2. Because in the case where it's even, we get n over 2, and in the case where it's odd, we get n minus 1 over 2. Or, yeah. There we go. OK. So the point is that what we're doing when we do this proof is that we're both doing a proof and writing a function at the same time. And this is the idea that proofs have computational content. And so this was a proof in Cubicle TT, which is a proof assistant developed by Kokand and his collaborators that implements univalent foundations. And so what I want to talk about now is the sense in which it was challenging to implement univalent foundations in such a way that we can do calculations like this. Not just with natural numbers showing that everything's even or odd or something like that, but also calculations with homotopy groups of spheres, like we'll get to later in the talk. So the idea for computation is that in type theory, there's this notion of computation arising from expanding definitions. So if you have a function like even or odd, and you apply that to an argument, then you expect to get the body of the definition of the function. If you have a pair, like we saw in the recursive case there, and you take a projection, you expect to get the component of the pair that you put together. If you have a natural number, like 0 or successor, and you apply a function that does recursion on natural numbers to it, then you expect to get the 0 branch when it's 0 and the successor branch when it's successor. So your intuitive idea of how a program like the double function might reduce is exactly what we're doing when we do computation in type theory. And these are what are called definitional rather than typal equalities. And if you're thinking in terms of the simplicial model that Andre talked about on Tuesday, then the idea is that the definitional equalities think semantically of as the actual equalities in the simplicial sets, whereas the the typal equalities you can think of as the one simplices or the paths. And in ordinary type theory pre-univalence, all of the computation is definitional or exact equality, in the sense that I expect that if I define a function and then apply it to an argument, then just by expanding definitions mechanically in a way that the proof assistant can do for you, what you get out of that is the definition of the function. Okay, so that's a pretty good story, except when it gets to the identity type, the path type here, what we were doing was using the fact, in this example, every element of path n from k to k is reflexivity slash the identity. So if you go back to the code that I had here, you can see that for 0, the second component of this pair, which is the witness that 2k or 2k plus 1 is equal to n, is 0 in the 0 case, 1 in the 1 case, 2 in the 2 case, and so on. That is, the proof that 2 times 2 plus 1 is equal to 5 is just witnessed by 5, because the computer does the calculation and checks that 2 times 2 plus 1 is equal to 5. So we don't need to do a proof of that there. And this is the story about equality types that sort of was,
so
yeah.
In your example, I thought it's definitional, it's typal.
Well, so it's a typal equality that in each case of the induction is witnessed by definitional equality or reflexivity.
It's kind of reduced to
Right. Yeah, in each case it's reduced to definitional. Right. So this is the story that we told about computation expanding, computation being reducing when you apply a way of using a thing to a way of constructing a thing. And this same story was applied to the identity type prior to the homotopy interpretations. So if you think about the way of using the identity type, the idea is that if you have a family of type C, which you should think of as C being a fibration over A, and then you have a path in the base from A to B, and then you have something that lives in the fiber over A, then there's a thing over here in the fiber over B given by lifting this path to the top and transporting this thing over to that side, so that we write that as transport. And the idea of computation for transport was that if this path P is the identity, then the lift of the identity is the identity function. So that was the computation rule that was in type theory. This was the computation rule for the path induction principle that's been mentioned a few times, like in Emily's talk. And this is a good rule if you know that every path is ultimately the identity, because then you know how the behavior of this principle is defined on the identity. That tells you in any closed program, like when I apply even or odd to 7, what the path will be, and so I won't get stuck. But the problem then is that this gives you, well, before I get to the problem, let me just summarize. So this gives you what's called a canonicity theorem, which says that for every closed term in Martin-Liff type theory pre-univalence of type nat, so a closed term is one with no assumptions, so it has no free variables. It's like even or odd applied to 6 is a closed term because it's a closed function, a function with no further assumptions applied to a numeral like 6. What you want to know is that for any of those, there exists a numeral such that t is definitionally equal to that numeral, which says that when you have a closed term of type nat, you can run it and get a number out, right? That's what we were doing in the previous example. And this relies on the fact that for every kind of way of using a thing, we have a corresponding rule for saying how it reduces on an introduction. The problem when we come to Voevodsky's introduction of the univalence axiom is that univalence gives you a new way of making things. It gives you, in particular, a way of turning equivalences into paths. But if the idea is that every way to use something should act on every way to make something, then this spoils the canonicity theorem that was on the previous slide, because we've added a new way to make something without adding a corresponding new way to use things. Okay, so there was a question for computation with univalence, and there still is in some sense, which is, what does it mean to transport along a path given by univalence? Right, we'd like to extend this idea of canonicity to Martin-Liff type theory with univalence, this idea that we had of proofs being programs in Martin-Liff type theory pre-univalence. We want to extend it to a situation with univalence. And Voevodsky conjectured that this was possible. So he said in a talk in Gothenburg, I think the ideas of this were around before this talk, but these were the earliest slides I could find on his website that had a nice quote about it. He said, unlike many other axioms, the univalence axiom is expected to have computational content. In other words, decidable normalization, so that's this idea of canonicity, should be extendable in a certain sense to terms which involve univalence. For example, given a term T of type NAT constructed using the univalence axiom, there's an algorithm that produces a term T prime not using univalence, and a proof, a path, maybe using univalence, that the two are the same. And if you rephrase this a little bit, you can make it look more like the statement of canonicity that we had on the previous slide, which is you can think of it as a constructive proof that for any closed term of type NAT in Martin-Liff type theory with univalence, there exists a numeral k with a path from n to k. And that's because when he said in his formulation that there's a closed term without univalence, we already know that closed terms without univalence are the same as numerals. And so we can reduce to numerals here. So this is saying that you can run programs up to paths in type theory with univalence. And this conjecture has a couple of very nice, this way of saying the conjecture that Voevodsky developed has a couple of nice properties, which is that one, it says that computation is the same in all models, because if you're doing computation up to paths, that is, you have an algorithm that produces a path, an element of the identity type, then you can interpret that element of the identity type, which is witnessing the computation, in any model where you can interpret univalent type theory. And two, it says that the univalence axiom already, in some sense, implies how univalence computes. That is, we don't need to add any further principles beyond univalence in order to have enough proposite typal equalities, enough paths between terms to get from any closed term of type NAT to a numeral. Okay, so this formulation is still open. No one's proved this yet, to the best of my knowledge. But we have made some progress on these kinds of things that I want to tell you about today. Yeah?
Why would you think it's true?
Why would we think it's true? Well,
because you say you have these paths.
Right.
Somehow saying that somehow by induction,
Yeah.
the path gets simpler and simpler until it becomes...
It's saying that every path, well, I'll try to give you some intuition for why it's true throughout the rest of the talk. But I mean, one simple way to see why it's true is that if you look at the Hoffman-Streicher one-groupoid model that Mike mentioned yesterday that predates univalence and has a kind of very simple form of univalence in it, then that's all very constructive in the sense that you can read off from that exactly how the transport operation is acting on paths that arise from that thing. So like in a very truncated case, like a very simple case of one-dimensional things, it was true. And we now have much better evidence. But yeah, we'll get there. Was there another question?
Just to make
Yeah.
clear, do you mean by computational content?
Yeah.
So do you mean that you may simply replace the axiom, say, by a rule or something?
I mean that this statement of canonicity, which is that closed terms of type NAT are programs that you can run and get an answer out. Yeah. Okay, so the kinds of progress that has been made, I'll go over who did what in a second on the next slide, but just the kinds of things is that we have models of univalence in a constructive meta-theory, meaning that there's a model of Martin-Liff type theory plus univalence where the model is itself constructed in a constructive language, constructive mathematics. And with this idea that proofs are programs, if you can construct a model in a constructive language, then that model construction is itself a program that you can run to run these other programs. So that's a somewhat indirect way of doing things. We also have models of Martin-Liff type theory and univalence that are based on programs and operational semantics. So here the things in the interpretation of the types are really programs with a specified operational semantics in the way that computer scientists do that tells you how to run each program. And we have new type theories satisfying Martin-Liff type theory plus univalence that also satisfy this definitional canonicity property. So that's like passing to a new type theory where univalence is not an axiom, but somehow a defined rule with actual computational content in the way that people usually do things. And there's also several experimental new proof assistants based on these ideas. So this isn't homotopy canonicity in the sense that all of these results are about computation in particular models, but we do now have some particular models in which univalence computes. And whether this is sufficient or whether we should still be shooting for homotopy canonicity, a mathematical question is whether the new type theories that we get out of this can be interpreted in the range of models that you can interpret normal Martin-Luff type theory in. So for example, is there some flavor of these new type theories that's also the internal language of an elementary infinity topos, that kind of question. And the reason why that might be nice, at least if you're the kind of person who comes from this point of view, is that if you have definitional equalities, more definitional equalities, that makes your proofs easier to construct in the proof assistant because the proof assistant is doing more work silently behind the scenes for you than if you have typal equalities that you have to witness and transport along. Yeah?
First one here, once you have a model,
Yeah.
why doesn't that solve the problem?
Because that tells you that you can take the syntax of type theory, map it over here, and over here, according to the additional equations that exist in that model, every term is equal to a numeral, but those don't necessarily reflect back. So you could hope to prove homotopy canonicity by somehow reflecting that back to the syntax, but it's not automatic. Yeah, yeah. Okay, so these models are all descendants of the first constructive cubical sets model by Besom, Kokand, and Huber. And these are models in pre-sheaves on some cube category, and there's a bunch of different choices for cube categories. So for example, this is based on the free monoidal category and an interval, and introduced this idea of uniformity, which I'll say a little bit more about in a second. And there's a next model that was based on a different cube category and introduced some new tricks in constructing constructive cubical models. And then this was a cube category with connections and reversals and symmetries and diagonals and kind of the works. There was another, Thierry came up with another Kahn operation for the diagonal cube category that took a little bit longer to figure out, but eventually Anjuli and Favonia and Harper kind of came up with the key ingredient to make the universe work for that last spring, and so now we finished that one off. And in addition, there's this work on canonicity/operational models where you're actually constructing a model out of programs or proving this definitional canonicity property, which actually shows that these type theories have canonicity up to definitional equality. There's been work on interpreting higher inductive types, which haven't been mentioned too much, but are the way we construct spheres and things like that in homotopy type theory. And so, for example, there's work interpreting the higher inductive types in this cubical model and interpreting higher inductive types and giving a schema for higher inductive types in this cubical model, and some early work by Isaev on a syntax for a proof assistant where you have used this cubical idea to give a nicer syntax for higher inductive types than existed before. And some of this work, like the work by these people, addresses the issue of having non-fibrant types and exact equality, as in Voevodsky's homotopy type system, which he proposed as a way to have both the notion of typal equality or paths and also the notion of strict equality that occurs in the simplicial model. And another nice thing that's come out of this work is the idea of these internal language presentations by Orton and Pitts and Birkedal, Spitters, and other people, where you work in the internal language of the one topos of cubical sets, and in that setting, you can express fibrancy as an internal formula. So you can view being fibrant as sort of a property of a type that you can express and work with. And this lets you, one, formalize these models in a proof assistant in a very nice way, and also, two, gives you another approach to having a mixture of fibrant and non-fibrant types, because you can just live in a world where the non-fibrant types exist and identify via a predicate the ones that are fibrant. And then there's been more mathematical analyses of these ideas by Audi and Gambino and Sattler and other people, which kind of take the ideas coming up in these constructions of cubical models and present them in a way that might be more familiar if you're coming from a more mathematical background. So there's a whole bunch of stuff, and so I think the thing to take away from this slide is mainly that since Voevodsky's proposal of homotopy canonicity and Kokand's pioneering work in 2013 about this, there's been a pretty good 5 years of interesting mathematics developed in terms of understanding how to make constructive models of univalence. So one of the consequences of Voevodsky connecting the homotopy theory side to type theory and formulating univalence is that we've had this very interesting line of work coming up in the last 5 years. So the basic idea, I won't go through the technical details, but the basic idea of these cubicle models is you have some kind of con-filling operation. So you have the idea that if you have some lines, then you can compose them to get a line that you might call go down, go over, go up. And there's a face, a square relating these two. So that's called the composite and then the filler. And then you have this for any dimension. So if I have a box with 5 sides, then I can make a lid for it and make the inside of the box. And then it gets a little bit complicated when you're trying to be constructive in the sense that you're taking presheaves on sets to the COP for some cube category C. And you might think of the cube category as being the free monoidal category on an interval object, where an interval has endpoints 0 and 1. But you can also take it to be the free Cartesian category or add in the connections and reversals if you know what those are. And then, so there's these choices, unlike simplices, where there's kind of like a canonical simplex category. There's these choices of exactly what you're taking presheaves on. And then when you're trying to be constructive, being fibrant is an algebraic or specified operation in the sense that for any filling problem, there is a chosen lift that you're actually defining an algorithm to compute. That's what makes this all constructive. And because of that, your goal is to define algorithms for these lifts in each of the types in type theory. So type theory has pi types, and you have to show that if you take a fibration and then a fibration over it, then the pi of those is fibrant in this sense. And it has sigma types and path types in the universe, and you need it to be fibrancy to be closed under all of these operations. And that requires a relatively careful choice of the definition of fibration. So to be constructive, it's sensitive to things like being stable under change of base in a strict way, or having certain cofibrations or certain trivial cofibrations exist. So you can take the cofibrations to be all monomorphisms like you would ordinarily think, except for constructivity, you want them to be all monomorphisms with decidable image. And then for certain choices of the cube category, it's important you can identify kind of the minimal set of cofibrations that allow you to push the construction of the fibrancy through for each of these types. Well, I don't know if it's minimal, but you can identify a sufficient set. But that differs for different cube categories. So for one of them, it's very important that the diagonal map on the interval, which lets you attach things to the diagonals of squares, is a cofibration, whereas for others, that doesn't come up because the connections replace that. So there's a little bit more fine structure here because we're trying to be constructive and chosen about these lifts than if you just say, I take the ordinary horn fillings in simplicial sets or something like that. And so the known, people always ask why not simplices, why cubes? And I don't have a perfectly crisp answer to this, but the methods that I know use the fact that the path space in cubical sets is defined by an operation on the base category, a functor on the base category of tensoring with an interval, or a to the Yoneda embedding of I in the Cartesian setting. And the fact that this has a right adjoint comes up in the construction of universes and some of the things we do to make the universe closed under composition itself. So this is not true in simplices, which is maybe some indication for why cubical rather than simplicial. And then Sattler has shown that you can build type theoretic model structures, which means now that the type theory is sort of based on a notion of filling problem and fibration against it, you can build a model structure where those filling problems are the cofibrations and fibrations, and then derive a notion of weak equivalence. But it's unclear if there are any of these cubical models where that gives you the same homotopy theory as simplicial sets or topological spaces. And Sattler's shown that some are not, but I think the question's still open for some of them, or the question of can you take one of these and fix it in some way to make it equivalent, or carve out a subset that is. So there's interesting mathematical questions there. Okay, with that done, if you want to know more about this, there's a couple of good talks, several good talks online about these sorts of things. So there's this nice hot electronic seminar series that Dan and Chris run. And there were talks by Thierry and Carlo and Julie and Favonias coming up in a few weeks. And then Bob Harper gave some lectures on their computational approach to this, where the elements of the model are actually programs at a summer school last summer that you could watch. Instead of going over the details of this, which gets a little bit technical if you're not already versed in type theory, what I want to do is show you some examples of, pop up back to a much higher level, show you some examples of computing with univalence in some things, just so you can see how using this line of work on cubical models Vladimir's ideas turn into running code in proof assistance that we didn't have before. So the first example that I'll do is an example of running the equivalence principle that Benedict talked about in his talk. So this was the idea that equivalent structures are now sort of automatically related by paths in homotopy type theory. So to make some examples of that, I'm going to go through a few different definitions of the integers in type theory. So the most basic one that a type theorist would come up with if you sort of ask them off the top of their heads is to define the integers, you take it to be the coproduct of two copies of the natural numbers, which you can think of as the non-negative and the negative numbers. So the right half is 0, 1, 2, and so on. The left half is -1, -2, and so on. But if you do this in the obvious way, there's sort of a little bit of a notational problem, which is that the right injection of 0 is 0, whereas because we're starting the negative numbers as a copy of nat, -1 is the left injection of 0. And so it's a little bit hard to read there because you're kind of shifted by 1 there. So you might take a different definition, which is instead to take the push out of two copies of nat, or the wedge of two copies of nat, where you glue the zeros together. So we can do this with a higher inductive type. The idea being that instead you have in left of and in right of 0, both representing 0, and then read right injection as positive and left injection as negative, and you go like that. Another way to define the integers is you can take the standard definition of the pairs of natural numbers, where you think of it as representing their difference. So 0 is 0, 0, also 1, 1, 2, 2, and so on. And 1 is 1 minus 0, 2 minus 1, and so on, right? So do difference pairs there. We can define that. Another definition that you can do is you can define it to be the free group on 1 generator. So 0 is 0, or the predecessor of successor of 0, or the successor of predecessor of 0, and so on. There's a lot of elements of that equivalence class too. And then another definition is you could define it to be loops on S1. And for the record, this is not the definition we used when we proved that the loop space of the circle is the integers. OK, so point being, there's many different ways to define this concept. And the idea of the equivalence principle is that these are all equivalent, and we can prove that they're all equivalent internally to the type theory. And we might want to use different ones at different times. For example, this is a good one to use if you're trying to prove that the loops of the circle are the integers. And we want to be able to mediate between them. So why might we want to use different ones? Well, if you look at the kind of canonical form definition 1, which was just the coproduct of two copies of nat, defining addition on that is a bit messy, because you get cases like, if I'm adding -1 minus a and -1 minus b, then that's equal to -2 minus a plus b, where it's coded like this. And remember that in left builds in a -1, so -2 is really in left of 1 plus a plus b. And you have to do 4 cases here to define addition. And so then when you're proving, for example, associativity, you have 8 cases. And they involve a kind of weird auxiliary operation of a subtraction that takes a natural number and another natural number and produces an integer. And you have to prove that that does the right thing relative to addition and so on. So it's nice in the sense that there's only one representative of each equivalence class. It's not so nice in the sense that you're always working with these normal forms. On the other hand, if you use the differences of pairs of numbers, then addition is just defined by the product addition. So like ab plus a prime b prime is add in that component in that component, along with a proof that it respects the quotient, which is where you kind of hide the mess in this definition. And then associativity is really easy because associativity for integers just reduces to component-wise associativity for natural numbers, which is an easy thing to prove. OK. So different definitions. One of them has nice normal forms. It's easier to work with sometimes. If you're mapping out of it, it's a great thing to map out of. This definition is nicer if you sort of want to reduce your problems to immediate problems on corresponding problems on natural numbers. So in type theory, we can prove an equivalence between these two definitions. So we do that by defining functions back and forth. So for example, so ZD is the difference of two natural numbers. So we send the difference of AB to A minus B, because that's what it represents over in the other representation. And then we have to prove that it respects the quotient. And there's a little bit of noise here, because in homotopy type theory, we want to define the difference as the set quotient, which means we need to put in a path constructor that set quotients things. And so we have to show that this Z is a set when we map into it, but that's true and that works there. And then for the other representation, if we have the negative part of the coproduct, we send it to 0 minus 1 plus n, and we have the positive, then we send it to n minus 0, and that's going that way. And so then we can prove that these two are mutually inverse. And so with univalence, what we get out of univalence is the fact that there's a path in the universe between these two definitions constructed by this equivalence. And what that means, the force of having a path in the universe, is that anything you can do in type theory respects that path. Okay, so what's something you can do in type theory? What's something that can be defined for one and then transferred to the other and or vice versa? Well, if you think about the definition of a group, right, when you phrase that in type theory, you say that it's a type that consists of a binary operation with a unit, with an inverse, and then if I do the unit and then it's the binary operation with the unit, it's the identity, and it's associative, op xy is the same as op yz, x, y, z, and that associativity, and it has an inverse, and the inverse is an inverse, and so on. Okay, so I'm just parroting the definition of the group. The point is that this is a thing that takes types and produces types, which means that via univalence, it should be automatically invariant under equivalence. So in type theory pre-univalence, whenever you have an equivalence between A and B and a construction on types like this group structure construction, then you can define by hand an equivalence between group structures on A and group structures on B. And what do? Well, you do the obvious thing. You take, if you want to define the multiplication in B, you take the multiplication in A, send the things over to A, multiply them, and send them back. Okay? But the thing that's a little bit sad about this state of affairs without univalence is that you can't write down anything in the syntax of type theory that's not invariant under equivalence. Right? All the formulas that you can write have this property that they're invariant under equivalence. And yet, for each specific thing that you do, you have to by hand show that it's invariant under equivalence. So univalence can be thought of as taking that thing that you can do by hand for each individual thing. And this is another intuition for why it should be constructive, because when you consider any particular thing, you know how to write out the transport along univalence. So what we're doing is instead we're saying that if you can make a path in the universe and you have a family of types, then when we define a group structure on one representation of the integers, for example, on the difference list, the difference of two natural numbers one, then we can mechanically derive a group structure on the other one by transporting along the equivalence. And so if we go to the code here, then this file here does all of that. And what we get out of that is, here, let me just page through it a little bit so you can see. So here is the definition that I had on the slide of the integers as the difference pair of two natural numbers. And then, well, there's some stuff. And then here is the equivalence between the two definitions. So the definition of Z as pairs of natural numbers representing their subtraction or normal forms, the coproduct where you've got one thing on either side. And then you need a couple of lemmas, and then eventually what you do is you prove that the composite of the two maps is the identity in that direction, and that the composite of two maps is the identity in that direction. And then once you've done those two things, then you get the fact that by using univalence on exactly this line here, that's in this isopath lemma, you get that this data constructs a path in the universe. Okay, so that's the extent of the code doing that. And then you can define addition. So here I've defined all of the group operations for the difference of two natural numbers, right? And that's the one that I said was easy because it just reduces to the corresponding addition and properties of natural numbers, and that gives you a group structure on this one definition. And then what we can do is we can transport that group structure along the path that we constructed by univalence to get a group structure on the other definition. And so rather than having to write out code that would be sort of proportional to the size of the type in question, we just write one line, which is group structure is a construction on types univalence says that we have a path in types, therefore everything respects it, and then we take our group structure on the differences of two natural numbers and get one on the other. And then because we have a computational model of univalence, we can, for example, ask what happens if we take the unit of the thing we defined up here for differences, which was 0, 0, and transport it along the equivalence to the other representation. Then we say that we get the unit being, oops, first I should load the file. OK, so we load the file, and that checks all of that. And then we evaluate the unit, and we get in right of 0. And then, which is the representation of 0 in the other representation of integers. And then we can ask what happens if I take take 1 and -7 and add them. Then if I add 1 and -7, then, and spell it correctly, then I get in left of 1, 2, 3, 4, 5 successors. And remember, negative numbers are shifted by 1, so that's -6 correctly. So what we're doing here is we're taking the definition for one representation of the integers, automatically transferring it to the other one, which is writing the code that I said you would write by hand. And then we can run it, and we can run it for the other representation. So that's the equivalence principle that Voevodsky developed, running on sort of the simplest example of that you can think of. And then the idea is that, of course, not just that you can do this for set level structures where you have a set and then like integers, and then are lifting that to another set, like a group structure on that. But that this would work for example, for if you have a type and then you define categories on that type, then if you have two equivalent types, you get equivalent category structures. You could transport that kind of thing, and so on. All right, so this is just kind of the simplest set level example of that kind of thing. OK, so next bit where computation with univalence comes into play, since I have a little bit of time left, I want to talk about higher inductive types in synthetic homotopy theory. So what I was doing before was just a very simple example where you're computing with a set level structure. But we can also compute with types that are built up by points and paths, because we know how to interpret these higher inductive types in these computational cubical models. So for example, I can define the circle to be the free type generated by a point and a loop. So this says base is a point on the circle, and loop is a path from base to base. And then what we're getting is the free infinity groupoid, or the free uniform Kahn cubical set generated by this stuff. So we're freely adding in composites to this generating data, which means that we have the identity and loop inverse and loop composed loop, and a homotopy between loop composed loop inverse and the identity, and so on, as part of the structure that comes out of this definition. And the way in homotopy type theory that we then, for example, play out the universal cover of the circle, which is supposed to be a fibration over the circle whose fibers are z, where transporting along the loop adds 1 and transporting along loop inverse subtracts 1. So like we're defining the winding number by lifting a loop to the cover and asking for the other endpoint of 0. The way that we do that is we define a fibration over the circle by using the elimination rule that arises from viewing the circle as the free type generated by a point and a loop, and then mapping the circle into the universe of types, which we know by univalence has as paths in the universe of types equivalence. So here UA is the univalence axiom, and we're applying that to the equivalence that takes x to x plus 1, which is a equivalence between z and z, and turning that into a morphism, or a path in the universe between z and z. And that's how we code the definition of the helix. We say it takes base to z and takes loop to this equivalence. And so then, if we go to a file, then here in the circle.ctt, we've got the definition of the circle and the definition of the loop space on the circle as the paths from base to base. And then here I've defined composition in the circle using the Kahn operation that allows you to compose paths in any type. And then loop is loop, and loop inverse is negative loop, backwards loop. Loop 2 is loop compose loop, and loop inverse is loop compose loop inverse. And so then we define the winding number map from the loop space of the circle to Z by saying we'll take this helix, which is the one that's defined using successor of path, where successor path is the path induced by univalence, and then lifting and asking for the other endpoint of 0. And so if we load the circle talk file, then we can, for example, ask what's the winding number of loop, and we get in right of 1, good. And we can ask what's the winding number of loop inverse, and we get in left of 0, which remember is -1, so that's good. And we can ask for what's the winding number of loop compose loop inverse, and it calculates in right of 0, which remember is 0, so that's good. So we can see that we're unwinding loop compose loop by the fact that we're lifting loop to the cover, which adds 1, and loop inverse to the cover, which subtracts 1, and then composing those two equivalences, and that gives you the identity function. Okay, so we can now run these kinds of things. So, so I had some examples for the torus, just so you can see that this goes in higher dimensions, but since I'm a little short of time, let me skip those. So, well, okay, let me talk through them, but not show them. So not run the code. So the main point is that we can define the torus by a very similar sort of thing. So the circle was a type generated by a point in a loop. The torus will be generated by a point, 2 paths, 2 loops, and then a square that says that P compose Q is the same as Q compose P. And then we can write a function using the elimination rules that let you work with higher inductive types from the torus to the product of 2 circles by saying we map the point of the torus to the pair of the base points, one loop on the torus to the loop in one direction, another loop, one path on the torus to the loop in one direction, the other path on the torus to loop in the other direction, and then the square to the commutative square that has those 2 things on each side. So we're just playing that out. And because what we've said is that the torus is the free type generated by this data, we don't need to say where the composites go. That's sort of implicit in the principle that we use to reason about the torus, which is that it takes the composites to the composites. And so then we can define a map that sends the loop space of the torus to the loop space of the product of 2 circles, because we can loop the map from the torus to the product of 2 circles, and then loop spaces commute with product, so we get a map to the loop space of S1 across the loop space of S1, which is Z and Z. So this lets us count paths on the torus. And then, for example, okay, I do have time. We can take a square and ask for the diagonal, and then we could ask for what's the count of that map, or we could compose a square with itself, compose the face of the torus with itself in that direction, and then ask what's the count of that, and then we can compose the square with itself in the other direction and ask what's the count of that. And of course, if you're looking at the pictures, we should be getting 2 Qs and 1 P out of that, and 1 Q and 2 Ps out of that. And so if we go over to the code, then we can load the torus talk function. Oops. Okay. Something crashed there. Oop, bad syntax. Yeah, I know. Okay, we can load the torus talk function. And then, for example, load the file. Twice x here is the square on the torus that in the picture was composing the torus face with itself twice in the x direction. Well, composing it once, 2 torus x's in the x direction. And then we can say that if I ask for the count of the diagonal of twice x, then I get 1 p and 2 q's, which, if I did it correctly, is 1 p and 2 q's. And then because we're kind of in this con-cubical set model where we can compose things, we can also do things like compose the face with itself in this kind of U shape, which means composing up here, going down along this, over along this, up along this, and then back along that is one way to think about it. And then if you run that one, you see that you get 1 Q and 1 P out of it. So you can kind of make these more complicated shapes and calculate them. Okay, so why might you, as a mathematician, care about like us fiddling around with computing paths on the circle and the torus and things like that? Well, there's a lot of work on synthetic homotopy theory, so a bunch of things were done. A lot of this stuff was done during the IAS special year that Voevodsky hosted, or shortly thereafter, and there's been some bigger projects since then, like defining the Serre spectral sequence or cellular cohomology, or exploring some of the theory of higher groups, or higher Hopf vibrations, or real projective spaces, or free higher groups since then. But the example that I want to leave you with for thinking about computation with univalence is one where there's a calculation of pi4 of S3 in homotopy type theory by Guillaume Brunerie, who was a pre-PhD student here during the IIS year, special year, and then a postdoc here for the last 2 years before this one. And Guillaume's proof of pi4 of S3, the way it works is he proved in type theory that there exists a k such that pi4 of S3 is equal to z mod kz. And of course, we know classically that k should be 2. But if you think back to the stuff we were doing at the very beginning about every number is even or odd is there exists a k such that blah, a proof of there exists a k such that blah constructively includes the k, we should be able to run this proof and calculate the k. And the way the proof is constructed is that it takes the generator of pi3 of S3, views the S3 as the join of 2 circles, and then there's a main map which is easier to express in terms of the join mapping S3 to S2, and then you loop that 3 times, and then you use the fact that pi3 of S2 is z, which Guillaume had already proved using the Hopf vibration in a different proof. And so you can take this and you can compose together these, and then the k in this proof is the image of the generator of pi3 of S3 under these maps. So the hope, the idea is that if things are constructive and you're in this situation where you've constructed some maps and then you want to evaluate them at some generator and see what index comes out, then you should be able to just put it in and run it and get the answer. Okay, well, I can't show you this one running because as of yet, we can code this in cubical type theory, but it either runs out of memory or runs out of time after thousands of hours or something like that, or both. So while we have a implementation of univalence where we can, in principle, run things, we don't yet have an implementation where, in practice, we can run all of the things we might want to run. But we can hope that we might be able to do it. So there's a lot of work right now on different proof assistants for cubical type theory that are playing with different choices of cube categories and filling operations, optimized definitions of the filling operation, right? So this Brunerie number problem suggests that we don't just care that we can mathematically define these operations. We need the operations to be efficient enough that in the examples we run into in our calculations, we can actually run them and get numbers out. And so there's been a lot of work recently on kind of thinking about different ways to define the filling operations, and then implementation issues, and whether having a language like this one or this one with both non-fibrant types and exact equalities might help with these kinds of issues because that reduces the size of your terms and issues like that. So there's a lot of work on the computer science side right now about not just making univalence constructive, but making it actually efficient enough that in the examples where we want to run things, we can get the answers out. Okay, so just to wrap up, so there's other CS applications like something called guarded recursion or parametricity, or one of the flavors of cubical type theory is sort of compatible with effects because it's based on an operational semantics, or seeing if these kinds of computational ideas can be applied to a directed type theory like the kind that Emily was talking about the other day, and do examples where instead of transporting along an equivalence like we saw in the group structure example, you're transporting along a function. If you only have a function from one thing to another, then for some types you might be able to do the same kind of transport. And there's a lot of mathematical questions about these cubical models that people are investigating. For example, can we compare the homotopy theories of these cubical sets models with simplicial sets? Or can we interpret these cubical type theories that have these additional equalities that let us run univalence in models other than the cubical ones that they're kind of designed for? Does this say anything about Voevodsky's original homotopy canonicity? There's some technical things like, can you take univalence to be a definitional equality, which is what one approach to cubical type theory is shooting for, or can you define paths to be the path space to be explanation by the interval, and at the same time have a definitional transport on lifting of the identity is the identity kind of thing, which are sort of, both of these are things where if we could do it, it seems like it would be nice, but nobody's figured out how to do it yet, to the best of my knowledge. Okay, so the thing I want to leave you with is just the sense that thanks to Voevodsky connecting homotopy theory to type theory, and in particular introducing univalence, which kind of prompted this big question of how to compute with it, which led to a bunch of work in computer science on these constructive models of univalence that are really pushing forward our technology on thinking about pre-sheaf models of type theories and other related models of type theories in general and having other applications. And thanks to Thierry and his collaborators and other people's work on this subject, it's really an exciting time to be a type theorist because there's a lot of new type theories and new ideas in type theory that have come out of this collaboration. Okay, so thank you.